thank you very much. Also, thank the organizers. So I've never been to a seminar with so many people knowing our kind of geometry. So that really saves me a lot of introductions about the basics of height intersections. So my talk will be 5 parts. The first part is Kronecker limit formula. This is a classical formula about special values of delta function, Dedekind delta function. And then from this formula, we can derive some formulas about heights. So this part 2 is just like a restatement or maybe like a simple consequence of part 1, but using our kind of geometry. So now the third one is the main result. The formula for arithmetic degree. And then number 4 is about some other formulas. The last part is about the proof. I don't know if I can go to there. Really depends on the time. Okay, so we start with the Kronecker limit formula. So we take tau in the upper half plane, and then we take the weight 12 modular form delta tau equals Q. So the goal of the formula is to compute values of delta tau. Actually, absolute value, we can only compute the absolute value. And the absolute value is not exactly invariant because this delta has weight 12, not exactly invariant under the action of SL2Z. But we can put a factor there to make it invariant. So the better term is delta tau times y to the 6. So this y is, I put y here, y is the imaginary part of tau. So now this one is invariant under the action of SL2Z. So the formula is an expression of that one. And the other side, of course, it will be something invariant under the action of SL2Z. It turns out that it is given by an Eisenstein series. So this is the usual Eisenstein series. You sum over all co-prime integers CD. This y is the imaginary part. So this is not holomorphic. It's a non-holomorphic Eisenstein series. It is invariant under the action. So you can say that the weight is 0. Now, it has analytic continuation, functional equation. Now, for analytic continuation, turns out that the constant term is the term that grows the fastest. And the constant term, I put E0 tau s to mean the constant term is ys plus phi s y to the 1 minus s. This y to the s is the easy part. This part is like the intertwining part. Phi s is some function of s. So this is the explicit expression of phi s, some gamma functions, and the Riemann zeta function, zeta 2x minus 1 over zeta 2s. So that's straightforward from the theory. Just compute the Fourier expansion, and then this term you just compute it and make analytic continuation, functional equation, and then just analytic continuation. And the analytic continuation gives this part, the zeta functions, which is the important part here. Now, this one turns out to have a pole at s equals 1, so we expand it. So this is the pole part, simple pole. And then we have the second term, which is like the constant term at s equals 1. So this is like the second term. So it's the constant term. Now these are the higher terms as s goes to 1, of course. So the other parts of this E is actually holomorphic in S. So the only pole comes from this part, and this part behaves like this. So if we get rid of this term in this E tau s, then we get a holomorphic function in terms of s. Now, it turns out that the value of this tau, or actually absolute value here, is just given by this one, but minus the pole part. So the formula So that's Kroneker's limit formula. The absolute value of tau of delta is equal to essentially the second term of this Eisenstein series. So it is pretty surprising that this formula works for any tau. Not just same points, any tau. We have this formula. Now we go to the second part, and then the second part is about actually some consequences of this theorem. The first consequence follows my remark that this is surprising for any tau. So now the first consequence is just like we specialize to same points. So this is the interpretation. So actually, we have two ways to do the interpretation. The first way is take tau to be same point. Now the second way is integrate for all tau in upper half plane mod by SL to Z. So each will give us a formula. Now, to introduce the formulas, the two formulas, I'm going to introduce the Hodge bundle. Oh, I can use the other board. So let x to be the modular curve x1, the modular curve over Q. This is P1Q. So this modular curve, so that the complex points is xc is just the upper half plane mod by SL to Z. And then you put a cusp there. To compactify it. So now take L, the Hodge bundle. Hodge bundle. L. There are many ways to describe L. Basically, L is the line bundle whose sections are modular forms. And there is a way, just following Berger's talk, just the talk before my talk. I guess he will finish next time when you take quotient of the L2. But here I give you an explicit one over Q. So that will be OX minus 2 infinity. So infinity is the cusp. But this minus 2, to me, is basically the canonical bundle. Or canonical divisor. So this is the part of canonical divisor. But this L is not exactly the canonical divisor. We need to modify it by those ramification points. So the modifications are we plus 1 over 2 of I plus 2 over 3 of omega. So these are elliptic points. So in terms of the most famous graph, so suppose this is the fundamental domain, then I is this point, and then omega, the third root of unity, is this point. Now these are the only elliptic points. Now you put some weight there. This 1 over 2 is like 1 minus 1 over 2. This is 1 minus 1 over 3. 2 and 3 are the ramification indices in the quotient. And then we also put infinity here. So infinity is like the cusp. So that's the whole expression. Now you can also define it like coherently in terms of stack. So this x is just a closed moduli, but it associates to corresponds to a stack. And then for this stack, we have this universal elliptic curve, and then we can push forward the differential shift of the universal elliptic curve to the stack. Then we get a bundle, and then we further push forward to this x. So roughly, you just think it as the canonical bundle. So that's a long expression. I write it here because later, when we do the general case, we will see like the analog. But essentially, that's not exactly a line bundle because we have fractions in the coefficients. So this is not exactly in the Picard, but in Picard tensor over tensor to Q. So it's a Q line bundle, and the degree is 6, -2. Oh, sorry, not 6. 1 over 6. So now I'm going to put an integral structure and a metric. So the integral structure is fairly simple in this setting. We just take the Zariski closure. So we first have xl, and we go to xl over z. So now this is just P1z, because this is P1q. And this one, we just take Zariski closure of all these divisors, and then eventually we make it a line bundle, or maybe like Q bundle. Now we can also put a metric. This is the Peterson metric. So the metric is actually that one, delta tau y to the 6. So if f tau d tau, if this one is a section of L, then that corresponds to a modular form of Y2. So there's a little bit problem about the sections. Is this is cube line bundle, but you just it means you take the integer part and take the line bundles. So we can even do more. We can even tensor some powers to get weight k line bundles. But here, let's just say that one, or even no co-sections. Let's just put it that way. So then the metric f tau is just this tau LC. So this is the metric. So now, for our interest, we actually use delta instead of f. So actually use this delta, or maybe we just write delta. That one is delta tau y to the 6. This is like sections of L tensor 6. Okay, now we can state state our new formulas, the consequences of the original Kronecker formula. So the first one, we take tau to be same point. So let's assume it is of maximal order. Okay, so K over Q is quadratic, imaginary. So in that case, we call that point of XH. Let's write P. P is the corresponding point in XH. H is the Hilbert class field. Now then, now we just evaluate this tau is still the tau, but then in the formula, in Kronecker's formula, the left-hand side just becomes log of the section tau. We multiply by 6 to get to. Sorry, we take a square, and then that one is sections of L to the 12. So then the left-hand side becomes height of L. L bar. L bar means, so we have integral structure, we have Peterson metric, so we get a Hermitian line bundle. So it's that one, and then P up to a constant multiple. The multiple comes from first the degree of L, and then another one is this tensor power, because this delta is sections of L to the 6. So it's a multiple of that one, and then the right-hand side. Right-hand side, so this one, if we use this one and we compute it, we will get we will get L function L prime 0 eta L 0 eta negative. So it's roughly the L1. So this eta is the quadratic character associated to that quadratic extension. So I didn't write down the constants, everything. So, but now I'm gonna write down everything rigorously. So the formula is height of L P equals negative, or it's just that one. If we normalize everything, oh, so here we have some constant. Eventually they cancel. So this is the formula. So the height of the point is negative log derivative of L. So this one, this is essentially the classical Charles-Selberg formula. So this is the first way to convert the formula to heights. Or probably I will use this part. Since this is the easy part, I can erase them. Now the second part is integrate Kroneck's formula over xc. xc is just h mod SO2z. We have a star, but it doesn't matter. Let's put xc circle means no cusp. Using measure. So we need a measure, and there's a canonical one to use here. Measure is invariant under the action of SL2R. So if we integrate, then the left-hand side, since delta is essentially a section of L, then this integration eventually gives us the self-intersection of L. You also have this like finite part when you compute the intersection, but since this delta has no zero or pole at pole, so eventually we don't get any finite part. So I will just write down the result. So it will be degree of L bar squared C1 hat L bar squared equals negative. So this is zeta prime of -1 and zeta -1. The whole thing is the log derivative of zeta, Riemann zeta function minus a half. So this side is just like the height of x with respect to L bar. This is the log derivative of zeta. So the remark is there are two things in this formula. The first thing is like the extra thing. The first thing is the metric is not exactly a Hermitian metric because this infinity is a cusp, and if we put the Peterson metric, there's a singularity, but it is a mild singularity. Eventually, this self-intersection still goes through by the work of Bost, extending the Gillet-Soleil arithmetic intersection theory. And then this formula is derived by Kuhn from the Kronecker limit formula. So it's due to. So that finishes the interpretations of the formula in terms of heights. Now the next section is about the generalization, which is the main result of this talk. So now I'm going to put these two corollaries here. we're going to generalize the formulas, the two corollaries, to a totally real field. So now the setup is that f is totally real. And we denote by g the degree of f. Now we take a quaternion algebra. We want to get a Shimura curve, so at infinity, we want B to be split at just one place. So split at exactly one Archimedean place. Then we get a Shimura curve. XU over F. So again, my XU denotes the canonical model over F. It's already over F. So the complex points will be given by the uniformization. Only when X is a modular curve, we have cusps. In general, we don't have cusps. It's already compact. So here U is so U is maximal open compact. So it's the full level, because for modular curve, we take x0, 1 instead of small levels. If you want formulas for small levels, then you can map to the full level and use projection formula. Then you get a few terms coming from the level, like linear combinations of log p. Now we have Hodge bundle. So we put omega XU over F. That's the canonical bundle. Canonical sheaf. Now again, we multiply it by the ramification points. Elliptical points and also the cusp. So it's essentially the canonical bundle. Now we also put a Hermitian structure on it. So integral structure. So we have XL, that's over F. We can extend it to XL over OF. So everywhere we take the cos moduli instead of the stack. But you can also formulate the theory, everything in terms of the stack. So here we take the cos moduli, and there is a canonical model of that one over OF. And that one is by Zariski closure on this part. And this one is just extended by the relative dual length sheaf. And we also have Peterson metric. Still looks like this. Now we get a Hermitian line bundle, and Now we can generalize the formulas on the other board. So the theorems. Then we will have two theorems corresponding to the two corollaries. So the first one is about height of same points. So suppose corresponds to OK. This K over F is a same extension. So again, we want it to have like the full OK action in some sense. Now, then the formula says this height L bar of P equals L prime 0 eta L 0 eta So this is the main term. This eta is the quadratic character of the ideal of F corresponds to the quadratic extension. Now, this is the extra term. Those D's are the discriminants. This is the discriminant of B, which is just the product of the norms of the primes ramified in B. And this is the relative discriminant. You still want to take a norm to get something in Z. So this is the first theorem. Now, so it's really a direct analog, direct generalization of the first corollary. But now, this one has connections to some other conjectures and theorems, mainly the average Colmez conjecture, as mentioned in the talk of Andrew et al. So these are the remarks. So this eventually implies the average Colmez conjecture. So, and then is also, we already know that, proved independently by the other group, Andrew et al. Gorin, Howard, Madapus. So, and of course, from Andrew et al.'s talk, we know that this one eventually implies the Andrew-Oort conjecture for abelian varieties of, for Shimura varieties of abelian type, following the work of Zimmerman. As you can speculate, so in the average Colmez, the left-hand side is the average of 14th height. The right-hand side is essentially that one. So to deduce the average Colmez from this one, we mainly work on this part. So just change that one to the average 14th height. So I forgot to mention this theorem is due to me and Shewu Zhang. So that's the first theorem. Now, the second theorem is also similar, because we already have everything. We have the line bundle, the Hermitian line bundle. We have the Shimura curve. So it's just to write down the formula. We do degree of L C1 L bar squared. So that's the height or the normalized arithmetic degree. Now, the right-hand side is log of Dedekind zeta. So in the original formula by Kuhn, it uses the Riemann zeta function. Now here is the Dedekind zeta function. So that's the discriminant, absolute discriminant of f. Now, that term is still a term coming from ramification. Now, this is for the ramification of f over q, and we also have ramification of b. So the places split in b. And for this one, we have, like, of course, log nv. nv is the norm. But this av is tricky, explicit. There are two cases. I will only write down one case about that. I write a case if 2 does not divide v of dv. dv is the local different. If 2 does not divide the local different and take evaluation at v, then this AV is 1 plus if 2 divides that one, we get another formula. It's similar, still like a fraction, simple fraction. Simple in here, but if you put it there, then it looks complicated. So this is in my upcoming work. Here are some remarks about related works. So the first case we already know. This is the case f equals q, b equals m2. The modular curve case. Now, if we remove this condition, then the formula is still null by Kudla-Rapoport-Yang. F equals Q. Now, turns out that there are many results in other cases similar to this one. There are conjectures by Mayer and Rosner, and also there is a result by Horman. His result is not exactly for Shimura curve, but for Shimura varieties of orthogonal type. So you do need O and 2, following from Borger's talk of the classification of Hermitian symmetric domain. O and 2 over Q. So also up to log P for bad P. So the last one I want to mention is a different approach by Fricks and Sankarin. So their work is really like a comparison of this formula to another formula over Hilbert modular surface. Relate the formula on Shimura curves and Hilbert modular surface. For f quadratic. So it turns out that if we don't insist on Shimura curve, if here we relax the condition 1 Archimedean places, if we don't strict on that one, then we still get a Shimura variety, and which may be Hilbert or maybe not. But we always expect a formula like that. So, and then this side is still the Dedekind zeta function, but then this side may be slightly different.
So when 2 divides the local difference, I'm sorry.
2 divides the variation of the local difference. Yeah.
You still get some.
I still have a formula. It's similar to that one, but actually slightly more complicated.
Still a fraction.
Yeah, still like a fraction of the norm of v. I didn't write down here. It's like a similar one. So that finishes the main theorems. So now other formulas. So there are already a lot of formulas about derivatives of L functions in the literature. So the most famous one is the Gross Zagier formula. And then now today we have 2 other ones. And as far as I know, these are all the derivative formulas which are proved. So I'm going to review all these formulas. Actually, eventually we will have 6 formulas. Each derivative formula has a version of critical value formula and derivative formula. So the first one I want to make analog is the class number formula. This is the easiest one. So it's just L. Let's first do the degree P. So P is the same point. So like this is like HK. The degree is HK, which is the Hilbert class field. Or degree over K is HK. Over F, it may be that one or maybe twice of that one. Half of that one. So now that one is the class number. So let's restrict to F equals Q. It also works for F total real, but simplicity, F equals Q. This is the class number of K. So the class number formula says that one is given by the residue of the Dedekind zeta function. But actually, you can just use the quadratic character because the Dedekind zeta function splits. So we will get L prime, just L0 eta. So you usually use L1 eta, but by functional equation, we can move it to L0 eta. Exactly equal, almost equal, up to some simple terms. This is the first formula, class number formula. Now, this formula actually corresponds to term 1. So I write the degree F here to mean like really like the degree of the field of definition of P. But then the height is the arithmetic degree. So this is the degree. Now, this is the arithmetic degree. So now, this is the height. This arithmetic degree. So we change the degree to the arithmetic degree, and then the L function, the value becomes the log derivative. So you change the geometric case to the arithmetic case, then critical value becomes derivative. This is always the case. So this is the second formula. And actually also amazing, one amazing thing is that in the degree part, actually we normalized by, in the arithmetic degree, we normalized by the geometric degree. And the normalization is somehow appears here. Because that one is essentially like that one. Do we have a negative here? That this negative looks probably we don't, but it doesn't matter because like up to some constant. Up to multiplication by some constant. So now this is the first analog. Now the second analog is the volume versus the arithmetic volume. So it's going to be degree of L. L is the Hodge bundle as defined. Now the degree is the volume. Why is it the volume? Because this is essentially the integration of C1 of L, essentially. That's like a basic formula. And then that one you can more or less can be written as xc dx dy 2 pi y. So that's the volume. That's the meaning of volume. Volume of xc under the canonical measure. Now that one equals, again, up to some constant, zeta negative zeta f prime 0, no prime. It's that one. So the volume is equal to critical value of the Dedekind zeta function. So this is a classical formula which can be derived from the Tomagawa number of this B cross, actually the normal one part of B cross. And then we have this arithmetic volume formula, or maybe arithmetic degree. So that's that's the other analog. Again, you change volume to change degree to arithmetic degree, and then change the critical value to derivative or even log derivative. Points, that's -1. So finally, the Gross Zagier formula. So the analog of the Gross Zagier formula is Worth-Burgers formula. So the formula is L half pi chi equals period integral squared. So I will not make the terms precise. But this L function is also the L function for the Gross Zagier formula. And then we have the Gross Zagier formula. Then we take a derivative, and then we get limited height. So these are the formulas in the literature. And I took time to put all of them here because in the proof of this formula or even this formula, we also like use the setting of our proof of this formula. So have a few minutes, so I'll write a little. So it's the same framework to prove. So we first have this Gross Zagier formula of YZZ. So and then we have the formula for this height. And then we have the formula of this C1. All these are proved in settings. So we have this Shimura curve over total real field. And in the proof, the major part is to compute arithmetic intersection of generating series, and also derivative of some isomorphism series. So make computation, compare arithmetic intersection of the generating series as formulated by Kudla. So now the other one is derivative of some isomorphism series. So after everything is computed, then we make comparison. Roughly, we want that one to be equal to that one, but actually, it's not exactly the case. If the main terms of that one are equal to the main terms of that one, and that corresponds to the Gross Zagier. And for the other terms, those degenerate terms, those uncomputable terms, eventually we can argue by modularity, we still get some identity for the pieces here and pieces here, and then this give the formula 2 and 3. That's all for the talk. Thank you.